Oh, dude.
All right. So let's get going here. I'll kind of introduce. Also, sometimes these things are on, sometimes not. And it kind of has a weird echo. If whatever is the case, let me know because I can't hear it, even though you guys can. But today we'll kind of jump in, start looking at just some basic statistics. I'll probably show you a little bit of stuff in Excel, how we create different tables once we have a data set. So I don't think we got this far last class, but if I did, I'll probably go through this fairly quickly anyways. So this is just like an old Chicago Cubs roster data that I had. I just picked like 10 of the players. You've got the name, position, salary, right? So I try not to use a ton of sports data. It doesn't really matter that I did here though, because you can think about this could be any company, right? I could have employee names, the position at the company, and how much they're getting paid. Right? So say kind of synonymous with any business example we would see. We think about kind of the rows here, right? So the very first row is kind of naming the different things we're collecting data on. So, for instance, putting up row, right, we collect the player's name, their position, and their salary. So we'll call those. Or I might have to stand over here. There we go. Elements or observations. I'll never call them elements. I'll always kind of refer to them as observations. If you went over to the stats department, you might get some people there who use somewhat more like, I don't know, technical term of element, but for us, we'll kind of call them observations. Right? So for every single observation, we've collected data on these three different variables, right? So every one of our columns, you can kind of think about as a different variable. So there's some terminology that we'll kind of be using. So we had three variables there, and we can kind of categorize them, right? So we're going to put them into 4 categories. So I'm going to start out, and I'm going to get this slide, but I'll kind of maybe give you a little bit of an insight or a good way to kind of remember these different types. So we've got qualitative and quantitative variables. So qualitative, think not numbers. Right? So this is something that we're collecting information for every single observation about, but it's going to be like a label or some kind of word, right? Non-numerical. So this could be something like, you know, if you had a used car data set, this would be like the color of the car, blue, green, orange, right? Orange, I guess there's not a lot of orange cars, but you get the idea, right? Maybe like if I was collecting data on you guys recording eye color or hair color. Quantitative is kind of the exact opposite. It is numbers. Right, so we're collecting information on every single observation, and we're collecting some type of numerical value. Okay, so for the majority of the class, we'll probably primarily be focused on quantitative data. We'll also talk about a lot of ways that we can essentially turn qualitative data into some type of quantitative data. So assigning numbers to represent different colors or something like that. Okay, so those are our main 2 categories. Okay, well, you know. Here, if we have the used car dealership, we think of mileage on the used car. If I was collecting data on you guys, maybe I collect something like height, right? Centimeters, inches, however I record that. That's going to be a numerical value. Okay. So under each one of these different types, we've got 2 different types, right? So there's 2 types of qualitative and 2 types of quantitative variables that we'll talk about. The first one will be nominal. Okay. So if I'm thinking about kind of like a nominal variable is qualitative, but it's even a little bit more specific in that it has no intrinsic value. Right? So this would be something like hair or eye color, gender, if we recorded it. We go back to that data set with the roster data, the baseball position, right? It's just a word or a phrase, so it's qualitative, right? But it doesn't really tell me anything about that observation. I can't rank the observations based off of this information I collected. But I still might be interested in, you know, whether or not, you know, what the person's hair color is, what the color of the used car is, any of this, you know, any variable you can think of that might be nominal. We still might be interested in that characteristic. It's just we aren't going to be able to rank the data based off of it. There's no intrinsic value. And also, kind of just a precursor, and I went over this in my other stat sessions with a little more time. They only meet twice a week. But a lot of times in some of the survey data, we'll have gender data. It is outside the scope of my expertise to go into discussions about binary and all this stuff. For the majority of what we'll look at, it's usually just male, female, right? Obviously, it's much more complicated potentially, but for our data purposes, we'll generally see the variable look like that, okay? So we've got our kind of baseball positions was an example of our nominal variable. We'll also have ordinal variables. So ordinal variables are also qualitative, so it's still non-numbers, but they have a little bit more usefulness in that we can rank the data based off them. So there is some intrinsic value that we can get from these ordinal variables. So what's a really good example of this? Well, it might be something like at the end of the semester, you've got to fill out these student responses about your instructors. And, you know, I guess the question that we generally look at the most is overall, whether or not you think they're an effective teacher. You can go anywhere from strongly disagree up to strongly agree. This is a word, right? So I'm collecting data from the students, but it's qualitative, it's non-numerical, but it's ordinal in the sense that I know someone who answers strongly agree thinks that that instructor is a better teacher than someone who put disagree, right? So I can rank the observations based off of this variable I recorded. Now, within each response, I can't do anything, right? Like if I have two observations that strongly agree, I don't know who strongly agrees more, but I can kind of rank them at least based off of these different categorical responses that we can see. Okay. Does that make sense? Any questions on that? Shouldn't be too tough. Education level is another good one, right? If you ask them what their highest level of education is, I know somebody that has some college has more education than someone that has less than a high school degree. But if I have two observations that both responded to some college, I don't know who has more than the other unless I ask a follow-up, like how many credit hours did you take or something like that, right? Which coincidentally enough would be something like a quantitative variable, right? So really to rank them more explicitly, I'm probably going to need some type of quantitative variable. Letter grades are another good one. I'm just thinking about different examples. I'm throwing a bunch at you, so hopefully one of them kind of sticks and then you'll remember. All right, I know someone that got a B did better than someone that got a C plus. Two people that got a B minus. I don't know who had the better B minus, unless I've got some follow-up question where I gather some numerical value that gives me the percent they got in the class. So I'm kind of talking bad on qualitative variables, I guess, to a little bit. They're not quite as useful. They're still important and we'll still collect them, but a lot of the times we're more interested in quantitative variables because they allow us to calculate a wider array of statistics, right? So the first type we'll talk about is discrete. So this is going to be anything where I collect a response and there's gaps in between the recorded response that I would see. So the easiest way to think about this is I could see 1, I could see 5, I can't see 7.49, right? For the sake of this class, discrete variable you can think of meaning integer responses. So you can only see 0, 1, 2, 3, 4, 5, 6, etc. There's gaps in between. I can't see the decimal. So some good examples, if I ask someone how many siblings you have, 0, 1, 2, 3, 4. Hopefully you don't say 1.5. And I get that there's half siblings, but you shouldn't have literally half a person, right? So you can only have 1, 2, 3. There has to be integer responses. You ask somebody how many days a week they do something. So I drink alcohol. If I drank today, well, that's 1 day. I've drank 1 day out of the week. There's no fractions there. There's no decimal response I can see. I can only see what 0 through 7. So there to be completely complete. It doesn't just have to be integers. For the sake of this class, we'll think of discrete variables will just be integer responses. It could be something like where you have a production process where things are made in batches of 100. So maybe I only see 0, 100, 200, 300. Like there could be wider gaps. But for what we're going to do, we're just going to think about kind of integer examples. Okay. Continuous variables are the exact opposite. So there you can see the integer values 2, 5, but you could also see 6.492178, whatever decimal we want to stop at, right? So we've got two types of qualitative, two types of quantitative variables. Okay? So some examples, if I had a really precise measurement system, I could look at height and weight out to whatever decimal I want. We can think about salary, right? We've got decimals associated with that. I can think about that as a continuous variable. And that was kind of the salary was in that Cubs roster data if we want to think about another example. Okay. Now, sometimes at this point, I get a smart ass who likes to tell me that salary is discrete, technically. So why, given the definition that discrete means that there's gaps in between the responses I could see, why could you argue that salary is discrete? What's the first amount I can pay someone? 0. What's the second amount? 1 penny. But have a gap there, right? I couldn't see 0.005. So if you want to be real technical, right, you could think of like there are gaps there, but for the sake of what we're doing in this class, you can actually work out the mathematical proof that anytime we have decimals associated with the responses, we can treat it like a continuous variable, right? It's approximately continuous. You can you take the mathematical proof that in the limit, it is continuous. So for the sake of what we're going to do, anything that has decimals associated with it, we're thinking of that as a continuous variable. Okay? So integers are discrete, and then decimals, we can think of continuous variables. Okay. It's not too crazy. Any questions on anything there? Shouldn't be too bad. So I'll talk about a couple different types of data sets. I'll go through this pretty quickly because I'm not going to quiz you over this, but just to give a kind of precursor to some things we're looking at. So we've got three different types of data sets. So cross-sectional is going to be where we record information at one point in time. So this would be like if I had every single country and I collected information on their unemployment rate in 2020. One point in time, I've collected this unemployment rate variable for a bunch of different observations or a bunch of different countries. Time series is when I collect data across time, but for only one subject. Right? So there, my observations would be something like, maybe I collect data on the United States unemployment rate for each of the last 20 years. I've got one subject, the United States, and now my observations are like every single year. Right? So that would be time series data. Panel data is when I combine the two, right? So I'm collecting information across several different years, across several different subjects. So maybe for every single country, I collect their unemployment rate for the last 10 years, right? So I'll show you some examples of this here. So cross-sectional, this was just some population data. So I've got a bunch of different cities, it has the top 20 cities, and then I collect information at one point in time, which was the census. So I can kind of combine my cross-sectional data sets, right? This would be like a FBI, but I'm collecting at one point in time, this for every single kind of city here. Time series. Oh, here's another cross-sectional, right? In 2011, I've got GDP and education expenditures, right, for a bunch of different countries. One point in time, right? Now, just because I have one point in time, I can collect several variables, right? I can collect GDP, primary education expenditures, secondary education expenditures, but I've done so all at the same point in time, right? But I still have multiple variables. Time series data, I've got unemployment data here for the US, but here are the observations, right, are every single year, right? So I've collected information across several points in time with just one subject, the United States. And then I've got some old ISTEP score data. I think you guys are getting old enough where I didn't have you with. I had 5th to 8th graders ISTEP data for 2009, 2011. Notice I've got multiple subjects, student 1, student 2, student 3, but for each subject, I've collected data in several time periods, right? So I've got 3 observations for every single student here, as long as they were in Indiana school each of the 3 years. Any questions? So panel data is kind of like I took time series and cross-sectional and like smashed it together, right? And it's probably the most useful. Starting out, I'll probably be pretty easy, and we'll probably mainly be focusing on like cross-sectional data or potentially time series. But as we progress, we'll start looking more and more at panel data. So a little precursor with some terminology that we'll start using as well, and this will apply to Friday's class for sure. But we're going to have different types of data that we collect in the sense that sometimes we'll have population data and sometimes we'll have sample data. Population data would be, let's say I'm interested in the average income in the United States. If I went out and collected income data from every single person, that would be population data. That's hard to do, right? There's a reason why the census only happens every 10 years, right? It's expensive. A lot of the times I don't even know if I have it on this slide or the next. Yeah, so I'll come back to that slide, but right? Sometimes it's just very expensive, right? That's why we only do the census every 10 years. Sometimes it's just not practical. So think about, I'll use this example because I think it's a good one. But let's say I wanted to collect information on individual weights, right? So I want population data. I go to every single person in the United States and I weigh them and I record this all in this huge data set. And that's going to take me a while. By the time I'm done, what do you think is probably true about a lot of those weights I collected? right, up or down, right? So my data no longer is even accurate. So sometimes to collect population data, it's just almost not practical. Not only is it not feasible in terms of its, expenses, but it's not practical. Right? So a lot of times we have to kind of result in taking just sample data, all right? So sample data would be something like, I go out and I randomly select 1,000 people and I collect data on their income, right? And then I use that sample, right, to be what I think is going to be reflective of the population as a whole. So using statistics from sample data to make statements about the population as a whole, that's what we're going to call statistical inference, right? So descriptive statistics, this is something that really not going to use this terminology a lot. We're actually just going to break down the types of descriptive statistics we'll look at. So things like the mean, things like the variance. So this is more of an overarching term that we probably won't use very often. But under descriptive statistics, we'll talk about each one of those types and how we calculate them. I'll just take place over time. But the idea of taking that sample and then looking at the descriptive statistics from that sample and making statements or inferences about the population, that's statistical inference. And there's some issues with that, and we'll talk about them. You can kind of imagine if I'm only taking, say, 100 people out of the US, I might have just happened to oversample a couple millionaires. My average income would look way different for that sample than for the population as a whole. So there are going to be some issues that we'll talk about, kind of the size of the sample, how the data is collected, right? How we randomly select people, but all of that's kind of down the road. For now, we just know that there's a difference between sample and population data. Any questions? I know I'm going through this kind of quick. A lot of it's just kind of get some terms out there. So some of the more fun stuff. So how are we going to describe data? Okay. So the very first thing we'll look at, first statistic in a way that we'll look at is going to be coming up with a frequency distribution. Okay. So all frequency distributions are we count the number of times we see every single possible response. So a good example, if I've got letter grade data, I would go through and count the number of observations that the student got an A. And I got rid of plus minuses here to make it a little bit easier. Then I would go through, count the number of students in the data set who got a B. Then the number who got a C, so on and so forth. So for instance, right, the frequency for the response of getting the letter grade A would be 2, right? And then I go down, how many students got B's? Well, I can see from a small data set, 1, 2, 3. So I write that number down. Then how many we get who got C's, so on and so forth. Now with a data set with like what, 10 people there or 9 people? Pretty easy to look at this and do this by hand, right? If I had, let's say, I don't know, every student that I've ever had, and I have their letter grade, over, I think I have a file, I think it's like 1,500 students or something right now, just from stats, right? I don't want to go through and count that by hand. So this is where Excel is going to be very useful, right? So I'll show you a little bit today. For sure, we'll dive into it more on Friday about how we can use Excel with larger data sets to come up with something like a frequency distribution, right? Is this idea making sense here? So this is all with qualitative data, right? So letter grades, non-numerical responses, I can come up with a frequency distribution. Okay. Now to come up with a relative frequency distribution, this idea of relative, we can think about it's actually going to reflect the proportion of the data that has that particular response. If I go back and think about my frequency distribution, to turn that into a relative frequency distribution, I would say, okay, take the 2 students who had their response, they got an A in the class, out of, this is 9, right? So 4, 6, 9, yeah, right? Out of the 9 students, so the relative frequency would be 2 divided by 9, right? So all I'm doing there to convert the frequency to a relative frequency is dividing those frequencies by the total number of observations. Now, what that does, it converts that frequency into a proportion, right? Because if I don't know the size of the data set, and I told you, I don't know, I've got this student letter grade data, and the frequency for A's is 39. Okay, that's tells me something, but what tells me more is, well, if it was 39 A's out of 50 students, I know that's an easy class. If it was 39 A's out of 1,000 students, it's a tough class, right? So I might be more interested in the frequency distribution there. So all I do is divide all the frequencies by kind of the total number of observations. Now what this relative frequency represents is what we call a proportion, right? It'll be a decimal value, because at the very most, if every student got an A, what would my relative frequency be? Every single student got an A, then when I divide it by the total number of observations, I would just have a relative frequency of 1. Yeah.
Wouldn't that turn into a quantitative data?
Yeah, so our original data is the letter grade data. We're then going to turn that into a frequency distribution, which will be numerical, right? So we're calculating this numerical statistic from some original qualitative data, right? Excuse me. So yeah, the original data is still qualitative, right? It's the letter grades. When we look at the actual original starting data, we're then just creating numerical statistics from that. Right? It's a good question. Any other questions on this before we keep moving? So I think I have the full roster data from whatever, I think this was like 2015 or something. I just went through and counted the number of players that were in each position. The baseball team, how could I turn these into relative frequencies? Well, if I add my frequencies up, I get that there's 25 players on the roster. So to turn these into relative frequencies, I would just do what? Divide each one of these frequencies by total number of observations, or 25, right? And I could do that for every single position. And I'll show you in Excel. You can do this pretty quickly. So notice all my relative frequencies are decimal values, right? Because we said the highest the relative frequency it could ever be is 1. But if I add up, right, I've got every single position on the team here. So if I add up the relative frequency of every single position, or every single possible response I could see for that variable, what should those relative frequencies add up to? So I add all these up. Yeah, just 1, right? Why? Well, think about what's in the numerators here. The numerators are just the frequencies. If I add the frequencies up, what do I get? Well, I should have counted every single observation 1 time, right? There should be no observation where I've got their position listed as multiples. Now, maybe in this example, you get that's a little weird. Go to the letter grade example, right? They either got an A or they got a B. They can't get both, right? And so I'll count every single observation once. So when I add the frequencies up, I get the total number of observations. So if I add these up, I've got the numerators will add up to be the total number of observations. They all have the common denominator of the total number of observations. When I add these up, I'll always get the relative frequencies add up to 1. Okay. Any questions on that? A little bit tricky, but that's just kind of a helpful thing as we're going through working on stuff. It's a good way to check. You know, if you come up with the relative frequencies and they don't add up to 1, you know you made a mistake somewhere. Maybe you just hit a wrong button on your calculator or something like that. But so we've got these frequency distributions and we've got these relative frequency distributions, right? We can also come up with percent frequencies. Okay? So percent frequencies, if I've got, you know, for instance, let's say 5 out of 10 students got A's in the class. What would the percent frequency be there? Well, 5 out of 10, that one I think kind of intuitively you know is 50%. Well, the relative frequency for 5 out of 10 is 0.5. So how do I go from 0.5 to 50%? I just multiply everything by 100, right? So basically to get my percent frequency, I'll take the relative frequency and multiply it by 100. So another way to think about this is we're just moving the decimal 2 places. And this will kind of come up as we work through different examples in the class. Now, as we progress, we won't be looking at, or we won't be calling them relative frequencies. We'll be looking at proportions, but it's really those 2 terms are interchangeable. Right? When I come up with a relative frequency, 5 out of 10, that's 0.5, that is also the proportion of students who got A's. Right? But I then want to turn it into a percentage, I move the decimal point 2 places, 0.5 becomes 50%. Okay? Any questions on that? Shouldn't be too terribly tough yet. So I went out and got the 2021 leading causes of death. I know what a fun afternoon project that was. But you can kind of see here, I've got them ranked just to make it look a little nicer. And then I have this catch-all category of other. But basically, the CDC has all the death certificate data. It gets processed, and then they come up with the leading causes of death are. So you kind of see 2021, COVID was the 3rd leading cause of death. You know, some of these maybe should say. It had to be assigned one type, they probably had several, but I believe this kind of kicked out anything that had multiple causes. So these are only just like single cause deaths. We've come up with a percentage of deaths that come from each one of these different types of ailments or kind of reasonings. So for instance, how do I come up with that? Heart disease killed 20.5% of people in the US in 2021. Well, I just start with the frequency, the number of people who died from heart disease. I've got every single death here because I created this catch-all category of other. I've got every single death in the United States. So there's about what, 3.4-ish million deaths. So I would take the frequency for heart disease, divide it by the total number of deaths, and then multiply it by 100. So this would be something that starting on Monday, I might expect that you have your iClicker and you get it registered by Monday. We'll probably do like a dry run problems on Friday where I'll just show you how I can actually pull up the iClicker app and how we'll operate it. But just to give you an idea what the questions look like, right? Might be something like this, right? So generally I would kind of talk through how I came up with that 20.5%. And then I would ask, okay, what's the percent frequency here for cancer deaths? Well, I just showed you or talked through a way of how we would calculate that percent frequency for heart disease. I now would expect you to then come up with a percent frequency for cancer here. Now, when I'm looking at this, first of all, A is ridiculous, right? What's the highest percent frequency I could ever see? 100%. That'd be if everybody died from cancer, right? Now, so quite often give you some of these that are like, that's obviously not the answer, but you only know it's not the right answer if you know the principles behind what a percent frequency is, right? So even when you come to the exams, they'll primarily, they'll have some short answer, but primarily multiple choice. I'll do a lot of stuff like this, maybe not quite this egregious, but if you know the principles, right, you can kind of limit it down. And then even if you're getting stuck on a problem, you can make a pretty educated guess, right? Now, I also can rule out one of these other answers right away. Which one and why? Yeah,
34.
yeah, why?
Because it's the second highest, but it's not as much as 20.
Yeah, look at what we, yeah, so a lot of times when I ask you these, like on these IQ questions, I'll ask you a question where something we just did will also help you maybe rule an answer out. So I know that if more people died from heart disease, right, 690 is higher than 600, then the percent of people that died from heart disease is 20.5%, that died from cancer would have to be lower, right? And if I'm a betting man, I doubt it's as much lower that it falls to 0.18%. If I come up with this on my calculator and I don't think about the problem I'm answering, I probably forgot to do something. What might I have forgotten to do that I would come up with this? Multiply it by 100. So we're going to get, the formulas will get more complicated as we progress through the semester. So don't get too lost in the formulas sometime and hammer things away on the calculator. Sometimes take a step back and think about, well, is the answer I came up with, does it even make sense? And if it doesn't make sense, it probably means I just forgot a step, right? And then I go back, rework it. Oh, sure enough, I multiply it by 100, I get that 17.8%. Okay. And I'll try to point these things out in the different, topics and problems that we'll work through, just kind of ways to like catch really egregious mistakes. Because in Excel, we'll start doing things and it like black boxes it. So it does stuff behind the scenes and then it spits out an answer. Well, if we know the principles behind the statistic that we're calculating, sometimes we can catch a mistake that we made in Excel. Like Excel might still spit something out at you, but you entered it in wrong, right? You entered the formula in wrong, and so you're getting an answer that doesn't even make sense, right? I'll talk about those types of things so we can kind of double check ourselves to make sure that, well, we're not, we didn't forget something like multiplying by 100. Okay. All right. So I then went through, calculated the percent frequency for every single type of death here. We've now got frequencies and percent frequencies. Right? So I want to show these in a visual. Okay. And I think I just had that from the previous slide that we were calculating. These are our options, right? So I can put this into a visual by doing it a couple of ways. You've got bar charts and pie charts. So a bar chart, generally the ones I'll show you, are all kind of horizontal, right? So this would be something like, I've got my different causes of death. So I've got something like heart disease, cancer, every other single category that we had. I would then kind of think about, I could put my percent frequency here. And I think the percent frequency for heart disease was like 20.6. So then what I would do is on the y-axis, right, go up to 20.6% and kind of draw my bar up to that point. Right? And maybe I fill it in so that it looks a little bit nicer. And then I go to the next cause of death. We calculated that was like 17.8% was coming from cancer. So we go up to 17.8 on the y-axis there. And that's how high up our bar goes. And we just do this for every single possible response that we can see for our variable. When our variable was the cause of death, that was just going to be the different possible causes of death. Now to make that a little bit nicer, we also then, so we don't have too long of a bar chart, right? If I didn't have this other category, what's going to happen to this bar chart? It's going to start getting really, really wide, right? If I have every single possible cause of death, I'm going to start getting like really, really, really low percent frequencies from everything like past nephritis. I don't even really know what that is. So, anyway, so a lot of the times we'll create these catch-all categories so that we kind of can have a more, succinct looking bar graph. You can do this horizontally as well. You're just flipping the axes, but generally we kind of keep it as a vertical bar chart. You can also do a pie chart, which, I mean, how many of you have seen a pie chart, right? Like in like 8th grade science, like I feel like this was on like standardized tests that I used to have to take, right? But I could take this data. Let me see, I got one here, right? And I could put it into a pie chart, right? So the pie chart, oh, nice, okay, I can see what the biggest slices of the pie are. It's 25.9, which was other. Oh, okay, well, that makes sense. But the leading cause of death, would then really look like heart disease and cancer kind of leading the way. Even COVID, right? Kind of a visual see quite a bit smaller than those two leading causes. Right? So, if I'm a policymaker and I'm putting together a presentation, I'm trying to get money, and I'm with, the, I don't know, Heart Association of America. I don't know if that's a real thing, right? But like whoever's trying to do research on heart disease, they could show something like, look, this is the leading cause of death in the United States. Like, give us some money so we can like try to, start to alleviate the deaths that are coming from this particular cause. Now the bar charts do that as well, right? So here's a bar chart of these vertical bar graphs. Now here, instead of using the percent frequency, I just use the frequency. So my y-axis is going to be like the number of people who died. So sometimes that would be appropriate, right? Because now I can look here and say, man, 700,000 people a year are dying from heart disease. Like, that's a very big number, right? But maybe I want to like reflect, well, what percent of all deaths is that, right? So then I want to create a bar graph, not using the frequency on my y-axis, but my percent frequency. If I do that, I end up with the exact same graph, right? So why does this graph look the same other than my y-axis size are changed? Remember, how do we come up with my percent frequencies from the original frequency? At first, I had to divide everything by the total number of observations. If I divide everything by the same number, it doesn't change the relative size of each one of these categories. So think about it this way. 2 is half of 4, right? Everybody agree, right? If I divide both of those by 2, I'm left with 2 divided by 2 is 1, 4 divided by 2 is 2. 1 is half of 2, right? So dividing something by the same number, it doesn't change the relative size of those two numbers. If I then multiply everything by 100 to get my percent frequency, right? So I've got my relative frequencies now, dividing by the same number didn't change the relative size. And then multiply them all by the same number of 100 to get them into percent frequencies. Well, multiplying things by the same number doesn't change the relative size, right? 1 is half of 2. I multiply those both by 2. 2 is still half of 4. Okay? So multiplying and dividing them or numbers by the same number doesn't change the relative size. So it doesn't really matter what I use as my y-axis there. It's not going to change the visual, like the height of the bars. It's just going to change what information I'm giving my audience on that y-axis. And depending on the, just really depends on the situation, whether or not the percent is going to be more impactful than the actual number, right? Maybe with like the number of deaths, seeing that it's, 700,000 might be a little bit more impactful, right? Any questions on that? All right, so how did I come up with all these graphs, right? So I think that's what I'll show you next. So we'll take a little bit of an aside. We'll probably work on this on Friday. I don't think we'll get there quite today. But I believe if you go to the Files tab, I put up this in-class data, I've got this graphing data week 1. So I'm actually going to open this file so that when I save this work, it's going to save for me. So here we go. So graphing data week 1, you can download that from Canvas. Now, I would suggest not just viewing it in the web browser, like actual download the file and kind of work along with me. But once I download this file, I've got kind of my Excel open. So this is where I will start discussing Excel as though you've never seen it. Okay. So here I've got what we call the file that's open is the workbook, right? I'm not going to like quiz you on these terms, just to kind of give you a general idea of how Excel works. I can then create different worksheets here, each that have their own data on there, right? I can add one, right? Add a new sheet there. And actually what I'm going to do before I get too far, and if I ever do start working in Excel and I forget to do this, please remind me. I'm going to zoom in so you can actually maybe see what I'm doing. So we've got 3 different kind of worksheets here in my workbook. Let's go to the unemployment data. No, not unemployment. Let's do cause of death first, since we're already kind of looking at these examples. So I've got basically the 2 graphs that I had in the slide. So I've got my percent frequencies bar graph. I've got my just regular frequency bar graph, and I've got my pie chart. Okay. So how did I create each one of these, right? So I'm going to go through, and you don't have to necessarily do this because it'll just pop up multiple ones. But I'm just going to click on each of these graphs. I'm going to delete them, right? Because I just want to have the original data here. So all I'm going to do to create these bar graphs is I would select every possible response that I had, right? Or every cause of death, the frequencies, right? So just clicked here and highlighted these, right? Now, each one of these cells, and actually I forgot every single time I switch worksheets, I have to change the view. Once again, yell at me so you guys can see what I'm doing. But here, all I'm doing is left clicking and dragging it over those cells, right? So in Excel, we have cells that have references. So for instance, this is cell B2, right? And this is cell B6, right? So that's just how we kind of reference cells. That's how I would like tell you what cell to look in. Now, once I've selected those cells, I'm going to go to Insert, right? And I think on a Mac, it may not be on, I think you guys have an Insert tab. Yeah, so it's still an Insert. I'll try to remember the differences here. I'm not always going to remember off the top of my head, and sometimes when I have to Google it, but then you should have these chart options, right? So you can kind of see visually, looks like there's 2 here, right? So the one that we want, it's not the statistics chart. It's actually a column or a bar chart, right? So we'll click on this. We want a column chart. We could even make it 3D if we really wanted to get fancy. And then it automatically creates this chart or this table for me. Now I can play around with it and make it fancier. That's not really my goal in this class. Like I'm not going to be a stickler for like, well, did you have the axes titles on there? And I don't care, right? I just care that you can get it into a chart. From there, it's just learning formatting in Excel. And that's not, this isn't an Excel class. I'm trying to show you how to use Excel to calculate statistics or display information. All the pretty stuff is, that's just fluke that you get on afterwards. All right, so you've got this kind of like little plus sign up here. If you really do want to play around with it, you can go, okay, I want to add some axis titles here, and I can like rename the axis title to be whatever I want. I can change the font size by just going to home and just like I would, change the font in a Word document or anything like that. So that's as simple as it is to create those bar graphs, right? You select those frequencies, insert column chart. I could do the same thing. I'll move this out of the way. Get down here. All right, there we go. But I want to do a bar graph where I look at the percent frequencies. So how do I do that? If I try selecting here, oh, well, now I've selected 3 columns, right? So what I do is I first select my causes of death. I then hold Control, or on a Mac, you hold Command. And then holding Control or Command on a Mac, you would then select the percent frequency. So that's how you can select like columns that aren't adjacent, right? They're kind of separated by some other. So first select the cause, then hold Control, Command on a Mac, and select the percent frequencies. Now I go to Insert, my column chart here. Now I've got my column chart, but it's using the percent frequencies as my y-axis. Okay. Any issues with any of that or questions? Yes, this isn't too bad yet. All right, so I'm going to drag this down here as well. Oh. And we got one last thing. It's pretty easy, but I'm going to select that data again. So hold Control, hold Command on the Mac. You wanted a pie graph. Oh, there's a pie graph option here. How convenient, right? And then you can play around with this. You can add the data labels. And like I said, all that's doing is going to this plus sign. You can kind of select data labels. If you right click it and you go to like select, I mean, you can do change chart type. You can mess around with this. We're not really going to do anything there. If I asked you to create a pie chart, I just care that you can kind of get that pie chart up there. Any questions on that before we keep moving? So it's very basic. I think the graphing in Excel is pretty straightforward. The next thing, I think I've got a slide that has this, but another type of chart we might want to look at is a time series graph. So the reason why we like time series graphs is because we go to this unemployment data worksheet, right? So we were on the cause of death. Let's go over to the unemployment data. Let's make sure we can see it. So here, I could kind of drag my cursor. I could drag it all the way down. It's kind of a pain, select all this data. So I'm going to show you a shortcut, right? So if I go to the very first cell here, or where my variable starts, and I want to, look at these two variables, right? My x-axis is going to be the year, right? So instead of the cause of death now, my y-axis, every single kind of category here would be what year am I looking at? And then my y-axis value is what's the unemployment rate? So my x-axis variable has to be on the left, which I have the data conveniently organized like that. And then the variable that I want to graph on the y-axis has to be the second variable on the right. So I need to select both of these. Instead of doing it with my mouse, like let's say I had 120 years, or let's say, I don't know, I've got a data set that's got thousands of observations. How can I quickly select this entire column of data? So I'm up here in this first cell. I'm going to hold Control and Shift, or on a Mac, Command and Shift. Anytime I say Control, it's almost always Command on a Mac, just to make it easier, right? So Control and Shift or Command Shift on a Mac, hit the down arrow. Notice it goes all the way down to the very last observation. Hit the over arrow, it goes over to wherever my data stops, right? So a pretty easy way to kind of select both of those variables, right? So Control Shift or Command Shift on a Mac, and then it's just using my arrow keys, so I can go over and down. So now I'll go to Insert, and I've got these line graphs here, right? So if I go to the line graph, it's going to look like, oh, wait, what's going on? This doesn't look right. So the problem is that would be convenient if that's how we could create these time series graphs. How we're going to actually do it is just select what the y-axis value is. Then we'll insert that line graph. Okay, that looks a little bit more like what I would think about as a line graph, right? There's actually some movement. So unfortunately, kind of selecting both of those, it doesn't recognize that this is what you want as your x-axis variable. And it's just got numbers here. So what you have to then do is just select those numbers, right? So all I did was click on those numbers, right click, go to select data. Now notice here when it says, what are going to be my axis labels? Well, I mentioned before, what we want to be our axis labels is no longer like the cause of death, but it's just every single year. So I can then go to edit my axis labels. Instead of 1 through whatever, I want to select the dates or the years that I want to put on that x-axis. And I could have used the shortcut there as well. I was just kind of dragging it down to kind of show you. Right? So I've now selected all those years. That's what I want as these axis labels. Notice even after I select them, before I even hit OK, it shows me what my graph would now look like. So instead of 1 through 20 or whatever it was, I've now got 1991 all the way to 2020. Okay? So select whatever variable you want to be measuring on that y-axis. All right, I'll show you one more time. All right. So we'll hit OK. So all I did originally was select that column of data. Once again, Control Shift or Command Shift on a Mac. I inserted this line graph. Unfortunately, it doesn't read the years, so I clicked on those numbers. I then right-clicked, went to select data, and then edited these axis labels to be the actual years in which the unemployment rate was calculated, right? And it updates those for me.
Why do you keep going on the
What keeps going on the y-axis?
year?
So did you just select the unemployment rate when you originally created the line graph?
Yeah.
So when you clicked on this and went to select data, make sure that you're not hitting this and selecting it. You have to go down here and edit the axis labels, right? Because if you just start selecting the data, notice it's treating that as the original data I was using for the y-axis. Do you have axis labels option on the Mac? Let me see it. Yeah, you should have an. Yeah, so it's still the axis. Yeah, so you see where it says horizontal category axis labels? Select in that bar, right? Like, I don't know, it'd be like selecting up here, right? Here's this like little bar. You on a Mac, you have a bar that's right next to the axis label. Select like that area and then go and select your years. So that way it's putting in those cell references where those years are. It's putting it into that toolbar.
Okay, I got
You
it.
got it? Okay. Yeah, sometimes it's a little bit, things are a little bit wonky on a Mac compared to what I'm gonna do. So the reason why we like time series graphs is because I can now tell a very quick story. Once I have this graph, I can tell you unemployment was fairly high starting out in the 90s. It dropped throughout the entire 90s to be like an all-time low, a little spike, a little dip, and then shot back up in about 2009 in that kind of great recession. And then it fell from then really till about the pandemic, and then it shot up after the pandemic, right? I mean, lo and behold, right? People couldn't go into work. So that doesn't make sense, right? So I can like tell these stories, or I can quickly say like, oh man, what happened there? What happened there? Like, why did I see these spikes? And then I can go investigate, you know, why I might have seen spikes there, right? So it tells a pretty quick story over that time period. Okay. Any questions on that? All right, so I've got one more type of visualization that we could look at. I'll hold off and show you some other stuff in Excel, and we'll kind of start with this visualize class. So just some basic stuff in Excel that I want to kind of show you and get out of the way. If I put an equal sign in any cell, so I went to that scatter plot data just to kind of show you this. That lets Excel know I'm going to want to either do some math, right? Or you want to use a built-in formula, right? So maybe I want to do something like, what is 2 divided by 10, right? So the equal sign lets Excel know, okay, I need to do some math for you. What kind of math I need to do? I need to divide 2 by 10. I hit enter, tells me that 2 divided by 10 is 0.2. So I can just use Excel to do basic math, right? 4 plus 6 is 10. Now, another thing that we can do after we put that equal sign is do what we call use a cell reference, right? So maybe whatever the violent crime rate was in Alabama, I want to put that value in this cell E4, right? So how can I do that? Well, I know that the value 453.6 that I want to put here, I could type that in. So, but probably a better way, and as we start working more in Excel, you'll see like it makes life a lot easier as well, is to use a cell reference. So put this equal sign and say, instead of the number 453.6, I want to put, and I just click on that cell B2, and it automatically puts that cell reference in there for me. So this tells Excel, all right, there's an equal sign. So go to this cell, whatever reference that is, B2. Whatever's in B2, put that value over here in cell B4. So when I hit enter here, I should see 453.6. Sure enough, I do. So using these cell references I'll show you next class when we start dragging them and copying them down. There's some things we can do that saves us a lot of time by using cell references as opposed to just the number. But also notice, if I change the original cell I referenced, everything else updates. So this becomes really handy. Like I could use Excel to have like amortizations on loans. Well, then what happens if the percent changes? Every time I typed in whatever the interest rate was, I got to go back and change all of it. Well, not if I keep referencing an original cell where I could just change whatever the interest rate is. So here, well, let's make this like 897, right? If I change the value that's in that original cell B2 that I was referencing here, when I hit enter, it updates it, right? So this saves me a lot of work, right? Especially when there's things that like change over time, or I want to come up with some kind of easy like calculator to compute, what a payment would be based off of interest rates or something like that. So just a little bit of kind of an introduction to Excel. We'll take a kind of more of a deep dive into Excel, talk about how we do continuous data, how we can put that into a frequency distribution. Presents a couple more challenges, but other than that, make sure you get on and do that online quiz by the end of the day today. So that was the one that I talked about on Monday. It's just kind of a survey. If you have any questions, feel free to reach out. Otherwise, I'll see you on Friday.
And last question for that, basically what we're emailing you.